I'm going to be talking about Kubernetes multi-cluster networking. Um, this is a talk I did recently at Kubernetes Community Days in New York. Um, but I'm doing a slightly longer version of the same talk. Also, I think there were some recording issues with the audio and video with that conference, so I thought it'd be good to have new recording and go into some more detail as well. So that's what I'm going to do. And I did this as part of my work at Red Hat. Um, okay, so what we're trying to do here is sort of look at three kinds of things, as the title says, as the subtitle says, patterns, projects, and guidelines, right? Um, what are some of the key solution deployment patterns for multi-cluster Kubernetes networking? What are the different upstream and CNCF open source projects in this space? How do they compare with each other at satisfying these patterns? And what are some guidelines and recommendations that we can provide to keep in mind for people deploying these solutions? Okay, so let's see. Okay, so the agenda is a quick reminder of the problem statement. Why are we doing multi-cluster and so on? The solution patterns, the relevant projects, and some way of categorizing these and comparing these. Some details on their APIs, and then design recommendations and a quick demo. Now, I'm probably going to split this into two videos for this particular channel. So two or possibly even three. So let's do part one today. Um, this is a little bit about me. I'm in the emerging technologies group at Red Hat, and I have a bunch of experience in networking, cloud. And these days I've also been working on AI. Okay, so the scope of this talk is application networking, right? We're talking about applications that are containerized and also running in VMs, but are also spread across multiple compute platforms, primarily Kubernetes clusters and VMs. In this talk, we're only talking about the networking aspects, and primarily we're talking about CNCF and open source projects in this space. What we are not talking about is other aspects of multi-cluster architectures beyond the networking aspects, right? That would be that would be a bunch of separate discussions by themselves. We try to answer four types of questions. One, as we said, patterns, right? What are the key deployment patterns for multi-cluster Kubernetes? Projects, what are some of the relevant open source and CNCF projects, and how do we categorize them and analyze them architecturally? We'll spend some time on the APIs. How are these upstream APIs of these different projects related to each other? Maybe evolving, partially aligning, and guidelines and recommendations, and maybe more as we have future talks. But in today's portion, we'll cover maybe the first two, and then we'll go from there. So I mentioned that there are these other aspects of multi-cluster, and just for information, I'm providing a bunch of links on different subtopics like managing the fleet of clusters by themselves, right? There are projects like Open Cluster Management and others. Then there's application and workload deployment and lifecycle management across a fleet of clusters. Projects like Karmada, Argo workflows and rollouts. There's other kinds of multi-cluster operations, things like observability. So there's Thanos, Clusterpedia, Opni, and others. And there's projects that relate to better multi-tenancy and virtual cluster support and CRD management across a fleet of clusters. And projects like KCP and vCluster are in that space. So there's quite a few. And as you can imagine, this is a pretty diverse space. So you have to sort of think about all of these aspects when you're designing a complete multi-cluster architecture. And multi-cluster networking is just one aspect, although a pretty key aspect of multi-cluster solution architectures. So please feel free to refer to these kinds of projects for those other details. Okay. Let's remind ourselves, what are the primary use cases and why would we even consider doing multi-cluster? Um, so the first point is application high availability, HA, and disaster recovery, right? You don't want to keep on making uh, your cluster bigger and bigger and put everything in your enterprise in one cluster. You want to have, uh, if that cluster goes down, the blast radius would be everything in your enterprise. You don't want to have that. You want to have multiple clusters in multiple availability zones and even geographies for availability and disaster recovery. Second key question benefit is improved performance. If you're serving clients across many different physical geographies, the latency of serving is better when you're serving clients in two different geographies with services that are replicated across those geographies. Um, it also reduces costs in terms of traversing backhaul networks. Then there's data gravity or compliance requirements. Some state has to stay in certain regions, and so the services dealing with that state or managing that state also need to um, be in those regions. So that results in an application being spread out across multiple clusters and possibly multiple geographies. Other benefits include just infrastructure upgrades and application upgrades and rollouts. So, for example, if you wanted to have a very robust method of operation for just upgrading your Kubernetes cluster, maybe a good methodology would be to temporarily create a backup cluster, um, gracefully move all your services from your primary cluster to this backup cluster, completely delete and recreate your new primary cluster using your new software, your new Kubernetes stack, and so on. And then either migrate some or all of your services back. So having this ability to take advantage of Kubernetes replica sets and services and use that to improve your uh, uh, upgrades and operations is a huge benefit. And then finally, just it's almost inevitable. I mean, you will end up with many clusters across your enterprise. You'll have capacity in different places, and you may have various organizational reasons and resource optimization regions to spread your services across clusters. So there's plenty of use cases for multi-cluster. However, there's cost benefit trade-offs. You do not want to um, automatically decide on deploying fairly complex. This solution space can get pretty complex if you're dealing with some really complicated scenarios. So a key aspect is, what is the appropriate level of multi-cluster adoption given your topological and application constraints? And that is one of the key things that we are trying to answer in this talk. So let's start with talking about architecture deployment patterns, right? And some of the key decisions that you would want to make include how you're going to define your north-south multi-cluster networking, right? By that, we mean ingress traffic from, let's say, a web client to a web service running on your Kubernetes or virtual machine clusters. That's not south, but now across clusters, right? We're not just limiting to single cluster north south. Yeah, we have features like node port load balancing and so on, but we're talking about cross cluster north south networking. Similarly, there's cross cluster east west networking, which is essentially going um, quote unquote sideways between clusters. Uh, so it's service to service networking across clusters. Another key design pattern is the kinds of network topologies, right? Is it a single, are all your clusters running in a single flat network? Or are these multiple network domains that need some kind of NATing gateways to for traffic to be able to cross these different networks? And that definitely impacts a lot of your design pattern decisions. There's single mesh versus multi-mesh, right? So we'll see that in many of these multi-cluster networking frameworks, there's the concept of a mesh. Sometimes it can be a cluster mesh, sometimes a service mesh. Um, but do you want to put all your applications within one logical mesh, or you want to distribute them across multiple meshes within your enterprise? Similarly, there's trust domains, right? For the root of trust for secure networking connections such as TLS. Is it common across these meshes or these clusters? Is it different? Do you need to do federation across multiple domains? That's another design pattern. Operational needs, right? Is a particular solution, who's going to be operating that, what this framework, the solution? Is it primarily targeted at um, admin roles, IT staff and Kubernetes cluster admins and container networking admins? Is it primarily targeted at application development teams themselves, or some appropriate mix of the two? What are the organizational constraints across these clusters? For example, how are namespaces managed and allocated? So all of these actually do have significant influence on the kinds of solution you choose. Not only these, there's actually quite a few more, right? So there's things like, what are the kinds of traffic types your applications would need to use? There's of course HTTP. Do you want to have, will you have only TCP traffic? Would you also have UDP traffic that you want to run in this cluster manner? What about protocols like gRPC, protocols specific to certain applications like MySQL? Of course, there's IPv4 and IPv6. What are your available address pools? So all of those networking aspects are a key design pattern. Then there's, what are the kinds of endpoints you need to reach? There's Kubernetes containers, there's virtual machines, there's even serverless endpoints, right? Um, do your solutions work for all of these variations? How would you implement network policy across these multiple clusters and meshes? Um, how would you do service discovery? Discovering of logical services whose endpoints might be split across multiple clusters? What is the degree of zero trust, overall zero trust architecture support and zero trust networking in particular uh, by the chosen solution? So are you using cryptographically secure identities for the infrastructure and for the workloads? What are the different encryption options supported? So, both the security and the networking and performance aspects of all of these decisions. And then just what is the, community software and project status of these different projects, um, both in upstream communities as well as in the level of support by commercial vendors offering support. So you can see that there's a lot of architecture pattern decisions. Um, we'll focus on a couple of these, but then as we go through, this multiple talks in this series, maybe we'll be able to cover a little bit more. As you can see, we could be doing a lot of deep dives into each of these topics, and we'll see how much we can go into for each of these aspects. So let's look at an architectural diagram to understand some of these patterns. In this picture, we're showing, let's assume that there are 4 Kubernetes clusters that are in some way meshed together in a multi-cluster networking configuration. The exact details depend upon the particular multi-cluster networking framework chosen. And of course, we're going to talk a little bit more about those, but some of these aspects are actually common across all of these projects. So as we are trying to understand the patterns, I think we can use these common sort of architectural descriptions. So we have 4 clusters, and we talked about things like north, south, east, west, single network, and so on. So here we have cluster 1 and cluster 2 are running within one single flat network, right? In this picture, it's network 1. And clusters 3 and 4 are in another separate private network, right? Network 2 in this picture. So this overall solution has a mix of single network for some clusters, but it is effectively a multi-network topology, right? When we say network here, we're referring to a contiguous IP routing domain where any endpoint can reach any other endpoint in that domain without needing to get NATed. So all IP addresses are unique within one particular network. That's what we refer to as a flat network. But so in this case, any pod, the pod IPs for all pods in cluster 1 and cluster 2 are unique. So a pod in cluster 1 can directly network or can communicate to a pod in cluster 2 without needing to get NATed, because this is all in one network or one routing domain. However, when a pod in cluster 1 or 2 needs to communicate with a pod or a service in clusters 3 and 4, it cannot do that directly because these are on separate private networks. And one way to address that is to use east-west gateways, which are a common aspect of all of these projects that we are about to discuss. And that's how you would send them get, through an interim network, being able to communicate across these networks. So that's what we mean by sort of this single network and multi-network model. Also, this picture shows that there is north-south multi-cluster load balancing, right? So we talked about north-south networking as one key design pattern. So here there's an ingress gateway, which actually is able to load balance traffic coming from, let's say, external clients to services running across both cluster 1 and cluster 2, right? So it's a multi-cluster north-south load balancer. So that's the pattern we talked about earlier in terms of north-south networking across clusters. And we said earlier that there is, east-west gateways and east-west networking across clusters or even across networks, right? So that's what these logical functions would achieve. So, and then finally, there's also egress gateways and egress networking as to how do you egress from this group of clusters rather, this multi-cluster configuration out into, let's say, the public internet or any endpoint that is outside this multi-cluster topology. So hopefully this picture gives you a feel for some of the key patterns we described earlier. And then there's the additional patterns we mentioned in the previous slide would be, again, aspects of these, for example, whether these are all in the same trust domain or not, and so on. Okay, So let's now move on to one of these patterns, namely the north-south networking and north-south load balancing design aspect. So here we're showing two clusters, two Kubernetes clusters, cluster one and cluster two. And we want to set up a north-south load balancing solution that works. So what we're going to do in this case is we're going to fully duplicate an application across both these clusters. In this case, the application has three microservices. In this picture, R, G, and B, right? And we designed this topology and deployed in such a way that the application is fully duplicated um, across each of these clusters. And there is some infrastructure that takes traffic from a client, for example, client one, and redirects it to one of these clusters, but the client can equivalently be served by either of these clusters because the entire application is duplicated both in cluster one and cluster two, right? So we've achieved one level of multi-cluster networking by completely replicating the application across clusters and having some logic to distribute incoming requests to one or the other of these clusters. A particular solution that is commonly used is DNS-based load balancing. And we'll be, looking at one a little bit more detail of one of those, but we'll do a quick summary here. So here we've got these boxes labeled GC1 and GC2, which are global server load balancing or global load balancing controllers. And then INGs are referring to the ingress load balancers within those Kubernetes clusters, right? We also note that in this particular case, it is possible that these could be stateful applications or they could be stateless applications, and in which case the actual application state might be outside somewhere. Um, but everything that we care about is fully replicated. Um, you would typically want, in order to implement stateful application in this case, you might want to use a separate global uh, state management system, via things like uh, cloud databases like, for example, Google Cloud Spanner and so on, which can actually give you that multi-region database outside of the cluster, right? So there are some of those aspects, but what we're trying to concentrate on here is the fact that with this pattern, we can achieve the north-south multi-cluster load balancing via this control logic. And what this does is the controllers are communicating within themselves and programming an external DNS. Perhaps that is the AWS Route 53, for example, and having a particular URL or DNS zone delegated to these clusters themselves or these controllers themselves. So these controllers are actually acting as the authoritative DNS resolvers for particular application domains. So what happens is when the client asks for foo.com, these two controllers agree that, okay, for foo.com from this client, we are going to load balance it to this cluster and ingress the load balancer IP, externally visible IP for this cluster is 1111. For some other clients, they may agree and the DNS response would be the IP address of the other ingress cluster. So essentially, at a DNS level, you're getting different clients assigned to different clusters, but they're getting the full application um, at each cluster. Um, what happens when a particular microservice is unavailable in that cluster? Well, you have to have the appropriate level of um, failover detection, fault detection, health checking, and failover logic that the GSP controller is able to trigger a failover, and clients are able to get redirected to the other cluster when a particular cluster is in a failed state. This is actually one of the demos that we'll see at some point, so we'll see this in action. So essentially, this is one way of achieving the north-south global load balancing pattern. Okay. We've actually identified 4 different ways or 4 different patterns for implementing the north-south multi-cluster ingress pattern requirement. Briefly, those are listed here. So the first one is essentially just use an external load balancer appliance outside of your application clusters. So that appliance could be something running an open source load balancer like Terrific or Envoy, or commercial offerings from F5 and so on. And there's API gateways which do those kinds of functions as well. An issue with that is that the appliance then becomes potentially a bottleneck in the data path, because it's actually sitting in the path of the traffic being load balanced. And the external appliance also becomes a single point of failure, so it needs its own HA solution. But you may want to use the solution, especially if your enterprise is already using such a load balancer for other purposes, right? So very often an enterprise might already have, an F5 or an HA proxy load balancer, and you might as well use that. So that's sort of category 1 of solutions. Category 2 is building a Kubernetes native DNS-based global load balancer, right? Somewhat like the diagram and solution we described in the previous slide. So a CNCF project that does this is called K8GB. And there's also single vendor open source offerings like Quadrant, Glue, Kong Gateway, and a few others, right? So these are a little bit more Kubernetes centric than the external appliance approach. And they have various degrees of, multi-vendor support. So as we said earlier, the key difference is that these are, more likely to be open source and CNCF projects. They're more likely to be Kubernetes native. The one difference here is that one key aspect here is that you can get fine-grained per application failover. So you can actually decide that for foo.com/app1, we're going to redirect traffic to cluster 1, and foo.com/app2, we're going to redirect cluster 2. So you can get some fine-grained L7 path level failover and load balancing. But a drawback is that the failover performance is not always great and can be inconsistent. And the reason is that we are relying on clients to refresh their DNS resolutions, their DNS queries, and the DNS caches when there's a failover. And this is not done in a very consistent manner by a lot of host clients. So even though these solutions actually typically advertise a small DNS time to live, right, which is providing the client with the timeout after which they should be refreshing their DNS caches. Not all hosts actually follow that. And even many DNS servers and many DNS relays, they actually do not necessarily support fairly low DNS entry time to live, right? So default entry for DNS is typically in hours or days in many cases, but you can come down to 5 minutes, in many cases, but you still will see a little bit of inconsistency. So you might want to check on the kinds of clients and, the kind of DNS TTL support when you're doing with these solutions. The third solution is using an Anycast load balancer from a public cloud. So, clouds like AWS and GCP and essentially all of these public clouds, they offer global network load balancers, which allow you to advertise a single virtual IP from different locations, and traffic from different clients to that virtual IP can get load balanced to different backend locations, essentially achieving your north-south load balancer uh, pattern. This is a per IP based failover, right? So this is not an L7 based failover. Um, it tends to be a bit more expensive because you're using a more complex public cloud service. So these are services like AWS Global Accelerator, Google Cloud Load Balancer, which is based on their earlier project called Maglev, I believe, and CDNs like Cloudflare also implement similar Anycast load balancers. The benefits are very fast failover. These are essentially sub-second failover. You're utilizing the network, and the data path is scale out. So both in the approach 2 and 3, you do not have a single appliance as your load balancing bottleneck. You're relying on the network to do the load balancing. So you do not have to keep on upgrading a single device to higher and higher capacity. The network is essentially doing your load balancing for you, and you can build some really wide globally distributed patterns with this. And finally, the fourth pattern is a custom BGP Anycast. So analogous to the public cloud, but an enterprise can choose to build using BGP a similar Anycast solution where you have a virtual IP advertised by different locations and different clusters. And you can do that using CNIs that have the BGP mode, as well as with uh, Kubernetes cluster load balancers such as MetalLB, which also have a BGP mode. And both of these can be used to advertise a single virtual IP from multiple locations, and then have your data center network designed to properly load balance traffic to this virtual IP to the different locations. You do need to design, your data center does need to be designed uh, to make this happen, because you're essentially emulating what the public cloud load balancers do when they provide the Anycast service. So these are 4 categories. So we did have a blog almost a couple of years ago now on global load balancer approaches, where we kind of went into these different categories. So these are the patterns that you would consider when selecting a solution for the north-south networking multi-cluster pattern. This is actually another visual description of the cloud-based Anycast. Um, I've already described it, but this would be an example where this virtual IP 201.210 is being advertised by edge proxies located in New York City, Atlanta, and London. And the application, the DNS resolution maps to always to 201.210. So you do not have to worry about different end user clients uh, having inconsistent DNS cache handling, because the DNS resolution doesn't change. It is just that you get routed by the IP network to a different edge and then to a different backend. So that was a little bit about north-south load balancing pattern. Let's now talk about the other key pattern, which is east-west networking. This particular slide shows a basic east-west networking configuration. Again, somewhat logical, but applies to essentially all the projects that cover this space. So here we have an east-west topology where you have clusters 1 and 2. But in this case, it's not that the applications are fully duplicated across clusters. It is that each microservice has one or more replicas across clusters. And in some cases, there may be some other clusters in the group that may not have any replicas of a particular service at all. So we're essentially splitting the logical services by having some of these instances um, reside in other clusters. So in this case, the Greens microservice has two instances in cluster one and one in cluster two. Similarly, the Blue microservice has three in cluster one and one in cluster two. And here, in this case, we're depicting a simplified version of the east-west networking, multi-cluster networking pattern, in which there is a single network. So as we described earlier, that means that pods in network one, in cluster one, can directly talk to pods in cluster two and vice versa without needing any gateways or NATing, right? So these are all one IP routing domain. And we also observe something called namespace sameness, which is that the instances of a particular service are always configured in a namespace with the same actual name string in all these clusters. And you need that in order for things like Kubernetes RBAC and policy management to work correctly. So once you have those restrictions, or rather design configurations, this is a pattern you can use. There are details on how the discovery of the services and pods, backends, happens across these clusters. How does policy work? And some of that is specific to the projects, which we'll list out shortly. So here we've seen, in this case, a failure example where backend service B4 has failed in cluster 2. And the traffic that is being serviced for that application in cluster 2 is now load balanced to wherever other replicas of that class of that service exist. In this case, the instance B3 over across into the other cluster. So traffic actually coming in from this ingress into G3, in this case, actually gets then sent over the network to B3 and back, or perhaps not even back, right? So this is sort of the basic east-west networking. What we mean here is cross-cluster service-to-service traffic, where the services themselves have replicas across clusters. And then an additional complication would be if you have to do the east-west multi-cluster networking pattern, but this time the clusters are not in the same routing domain, right? So in this case, the pods in cluster 1 are in network 1, and pods in cluster 2 are in network 2. So they wouldn't be able to directly network. And you have these networking gateway functions, gateway A in this cluster and gateway B. And the routing and service discovery is aware that these clusters are now in a multi-network multi-cluster, and these adjust the service discovery and pod discovery to redirect the traffic across clusters to use the gateways. And depending on the particular project, you may either, and also depending on parameters such as whether the hosts are in a common network, routable network or not, traffic in this case from the pod G3 may need to go through both a gateway on the source cluster and the destination cluster in order to get load balanced to a backend of the Blue service. So in this case, the Blue path here shows traffic from G3 going through a gateway on the source cluster, possibly getting NATed, and load balanced, and then going through a gateway on the selected destination cluster, and then finally getting actually locally load balanced to an instance on the destination cluster. And in SYN configurations, the traffic can actually get sent directly out from the host network path, but it would typically still need to go through a gateway at the destination cluster and then get load balanced across. So you can make east-west work even if you are constrained to not have your clusters be in the same environment. And this is often needed because for cases when uh, you know you're using the same RFC 1918 private address for Kubernetes pods IPs across your enterprise, right? Because yeah, that's a typical pattern, right? You don't want to consume externally routable IPs um, by your pods. So very often they use common set of private IP addresses across clusters. But that means that, an IP in this cluster for B2 could exactly be the same IP for B4. And you cannot just route directly. You have to go through gateways. And you have to then do your service discovery, load balancing, and possibly policy in this configuration. And these different projects, they differ in their ability to support these kinds of topologies. Um, the final thing, pattern I'll discuss today for this particular session is that you can now actually combine these patterns. So we talked about the north-south load balancing, and we talked about the east-west. But you may want to combine this. So we said earlier, the DNS based north-south load balancing has the benefit that you don't need any cross-cluster networking. But it is subject to to the issues of the client's DNS behavior being inconsistent, and so the failover times being somewhat unpredictable. So to address that, you could do both. You could decide that I'm going to do north-south load balancing using the global load balancing cluster controller as before, and do the DNS load balancing. But I would also want to be able to um, detect and handle partial failures of services in one cluster, and be able to go to the east-west route in case my north-south load balancer ended up load balancing traffic to a cluster where the application was not fully healthy, right? So we mentioned earlier that the global load balancer cluster could have detected this failure and could have actually updated the DNS resolution, but the client may not yet have chosen to update its DNS cache, right? So it could be that the north-south load balancer did what it needed to do, but because of delays on the client side, it is still load balancing to what it was previously uh, assigned to. And meanwhile, there's been a failure. So although the north-south load balancer has done the right thing by actually redirecting client one to um, cluster one in this case, it takes a while for client one's DNS cache to get updated. And this could be minutes and potentially hours. In which case, you supplement your north-south load balancing with east-west load balancing in this manner. And now you've sort of got the benefits of both the DNS-based load balancing, which is simplicity for an east-west for north-south load balancing, and the fine grain and the scale out capabilities and so on. Whereas you've addressed to a large extent the failover performance issues. So I'll stop at this point for this particular session. To summarize, we described the problem we're trying to solve. We said, what are the kinds of questions we're trying to answer? We said, there's patterns and so on. And then we covered several of those patterns to give you a feel for what kind of decisions you need to make. And then we looked in a little bit more detail at the north-south networking, the east-west networking, and possibly combining the two. Let's look at the rest of these solutions in a follow-up call.